and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. We're going to get right into it today. We're going to take a look at Dalton's law of partial pressures right off the bat, and then we're going to use Dalton's law of partial pressure to show how we actually collect gases in a lot of our reactions. So hopefully up to this point, we've seen a lot of demos where, or at least a couple of experiments, where we heat a particular compound or we perform a reaction, and then we recognize, oh, hey, we're losing gas, right? And so what happens if we actually want to collect that gas, and actually that's the molecule that we're interested in? And so we'll show you how we apply Dalton's law of partial pressure at the end of this lecture, and how we actually collect those gases, and the technique is called water displacement, okay? All right, so Dalton's law of partial pressure. Here's the definition of what it is that you need to get down. So Dalton's law of partial pressure states that the sum of the pressure, right? So the total pressure, so let's just say the total pressure of a mixture of gas is the sum of all of the individual partial pressures of the gases in the mixture. So let me say that again. The total pressure of a mixture of gas is the sum of the individual partial pressures of the gases in the mixture. So let me draw a picture and actually show you what I mean here. All right? So I've got a container, and in the container I've got a total pressure. All right? So all of the pressure is equal to this total pressure. So I've got a mixture of different gases. So I've got the blue molecules here, and we understand the blue molecules will have collisions with the side of the container. And so if the blue molecule, which we'll call particle A, was the only gas present, then the total pressure would be equal to whatever the pressure of A is, right? Because that's where all my collisions are coming from. Well, what happens if I go ahead and inject another gas? So we'll make it a red gas here, right? The star red. And so now we have to understand the red and the blue molecules are both having collisions with the side of the container. Each of them has their own distinct pressure. And so now my pressure total is actually going to be the pressure of the particles from A and the pressure of gas B. Well, let's complicate things even further. Let's put some green molecules in the form of a check mark in there and say, well, this is my third type of gas. So we need to understand still my green molecules are still also having their own individual collisions with the side of the container, right? And so now I have to understand and recognize, well, now my total pressure is the combination of gas A plus the partial pressure of gas B plus the partial pressure of gas C. And this can go on and on and on and on and on. I can have any different number of gases in there, and I need to understand Dalton's law of partial pressure states that the total is the sum of each individual pressure. All right? And we read it to really understand, because each type of molecule has collisions with the side of the container, each has its own distinct partial pressure. And you need to make sure you get that down, right? Each type of molecule has collisions with the side of the container, so each has its own distinct partial pressure. The other part of that you need to understand is that those distinct partial pressures, those are, right, the partial pressures are directly related to the moles of gas present. And we should understand that by now. If I put more gas in there, I should get more pressure, right? I get more collisions. And so something else that we apply with Dalton's law is actually called a mole fraction of gases. Now, the mole fraction has this funky looking X symbol, right? And so if I'm going to look at, let's say, for example, the mole fraction of A from my sample up above, what that means is I need to calculate the moles of A, and then I would take the moles of A plus the moles of B plus the moles of C. And so essentially it looks almost like a percent calculation because it's part over whole again, right? Moles of the gas I'm looking at versus total moles in the compound. And so what that gives us now, what we're able to do with this and say, okay, well, if I want to know the partial pressure of A, and all I know is the number of moles of gas that are present in my system, then what I can say is that the pressure total is equal to, or I'm sorry, the partial pressure of A is equal to the mole fraction of A times that total pressure, right? And I can actually use the mole fraction to calculate the partial pressure of my given substance that I'm interested in. And again, it's because of this statement, right? Those partial pressures are directly related to the number of moles of gas that are actually present, all right? Okay, and so now that's Dalton's law of partial pressure. It's not anything that's too complicated. So now what we want to do is we want to take a look at water displacement. So I'm going to pause the video and I'm actually going to draw a setup for you. Okay, and so what I've got drawn here, you might want to go ahead and pause your video and get this sketched out, because I'm gonna use the explanation of what water displacement actually is and run through what this diagram is. So the reaction that I've got diagrammed here is actually a thermal decomposition reaction. So I've got potassium chlorate, when heated, will decompose to potassium chloride plus oxygen gas. And so what if I want to calculate or actually collect that oxygen from this system? Well, what happens is I'm going to go ahead and use, let's say, I'll use orange for oxygen, right? So as this is thermally decomposed, I get oxygen molecules that essentially get collected, right? They turn into a gas. They will travel down the tube. They'll come into the water, and then they'll actually bubble into the water, and then we'll end up with oxygen up above the water here, all right? And so what it does is it allows, because of the liquid and the water that's present, it doesn't let the oxygen escape, and it actually will collect it up here in what we call a water trap, all right? And so this is one of the ways, one of the general setups of what water displacement looks like. It can look like a lot of different things, but essentially we're using some way, some tubing to collect the gas, and we're going to trap it using some liquid and solid rigid container, all right? And so what we need to understand also is that the more oxygen that's produced in this particular water trap, the more water is actually forced out. Right? And so definitely very, very important, as more O2 is collected, more H2O is forced out of the water trap. Okay, and so what I'm going to do now is I'm going to take this water trap, and I'm actually going to draw it down here again. So this is H2O. We're still going to stick with my orange up here, right, as my oxygen molecules. And so we go back to Dalton's law of partial pressure. Well, we understand that my pressure total is equal to at least the pressure of O2, because I know that that gas is present in that particular water trap. But the other thing that I need to understand, and this goes back to understanding Boltzmann's distribution, that even though this water is not boiling, remember there are some small subset of those molecules that have enough kinetic energy and molecular speed to actually enter into the gas phase. So what we see is we actually end up with just a few water molecules up in that particular gas. So we need to understand that the total pressure is actually equal to the pressure of oxygen plus the pressure of H2O, right? So, and the way that we refer to this is that the pressure of H2O is actually referred to as the vapor pressure of water, and it is a known value. That one will always be given to you. These are table values. We know what the vapor pressure of water is at every single given temperature. And so we run our reaction conditions, and all we need to know is, hey, what temperature is the reaction actually at? And we can calculate or actually not calculate, but we can look up what that vapor pressure of water is for that particular temperature. And so since this becomes a known value, it becomes very easy using this particular method to calculate the pressures of the gases and the amounts of gases and determine how much is actually created. Because remember, if this gas is collected at non-standard conditions, I run into this gas stoichiometry situation where I need to use Pivner to correct so that the particular pressures and volumes to get a correct number of moles of oxygen that are produced. All right, so we'll run into that in class. I'll actually show you some examples of that, because I'm going to walk you through the first couple that you do so that you can carry the logic train through. But if you have some general questions about what Dalton's law of partial pressure is or what water displacement is, get those down. I'll see you in tutorials for those, and otherwise I will see you in class.